Okay, so today we are going to be jumping into 7.8 and 7.9. 7.8 is on representations of equilibrium. A representation is, code for picture. So we're looking at pictures of equilibrium. Nothing too complicated. AP loves to use like pictures of chemicals and pictures of molecules and pictures of reactions. Generally, the rule of thumb with those is, you're counting, like literally counting to make sure you've got the same quantity on each side, right? If my reactant side has 8 oxygen atoms, my product side better have 8 oxygen atoms. So they will use pictures. There'll probably be at least, 2 or 3 multiple choice questions on the AP test that literally are pictures. I mean, different contexts, right? One might be an equilibrium context, one might be acid-base reaction or something. But the pictures are generally, you count up what you got and you make sure you got the same on both sides and you're kind of good. Okay, so 7.8 is really, really quick. 7.8 is kind of here and gone in like the next 5-ish minutes. 7.9 is on Le Chatelier's principle. That hopefully sounds familiar. Do you remember that Frenchy dude from last year? Vaguely. Okay, Le Chatelier's principle is basically the whole crux of what equilibrium is. Okay, so we'll look at that and we'll analyze different problems using his principle, trying to figure out which way the reaction is going to shift. We've done the whole Q versus K thing now for the last, 4 or 5 days in class. Le Chatelier's principle is a little different, but we can also relate Q to Le Chatelier's principle. We'll do that tomorrow. That's 7.10. Okay. So anyway, without further ado, let's look at some pictures. So it's very common for AP to represent all types of chemical reactions with pictures and graphs. I was just saying that. Reversible reactions are no different. Here are 2 graphs that you may potentially see. Okay, so here we go. We have a reaction. It is a reversible reaction. Hey, how do I know if it's a reversible reaction? Yeah. There's an arrow going that way, and there's an arrow going this way, implying that both directions are perfectly possible, right? So reversible just means that either direction can happen, does happen, will happen. What's equilibrium again? Nice, yeah, it's the same rate, okay? Not the same amount of stuff, right? I could have drastically different quantities on either side. Equilibrium is when the rate of the forward and the rate of the reverse are the same. Meaning, however fast I'm producing the products, I am as equally fast producing the reactants. All right, so here we go. We have 2 graphs. And I kind of showed you these graphs earlier. I think it was in topic 7.1, okay, a week ago. Concentration versus time. If you look at a concentration versus time graph, and you're trying to figure out when equilibrium is reached, what you're looking for is the point in time where the molarities are no longer changing. Okay? If molarity is changing, at any point, you're not at equilibrium. Equilibrium is established when the rates are the same, and the molarities do not change after that point in time. So this graph is probably the one they'll give you on a multiple choice question. And they'll say, at which point in time does this reaction reach equilibrium? And then it'll be like, at that point, or at this point, or at this point. Or they'll give you a 4th option that's like, cannot determine based off of the information provided. Okay? And a lot of people are going to say that, because it just kind of feels right. You know what I mean? Like it feels like, oh man, they crisscrossed. That's got to be important. Jake, need help? Who's trying to paper cut your hand? It's not paying attention. Well, I mean, you are. That's why. Yeah. You're good. So that point in time feels really, really special, right? If you look at that graph, it looks like the most important point in time. But if we're talking about equilibrium, please remember equilibrium is rate, right? Equal rates going opposite directions. This is representing equal concentration, meaning equal molarity. Our y-axis is molarity or concentration. So at that point in time, my reactant, which is this one going down, and my product, which is this one going up, crisscross. Great, they have the same molarity. It's the same molarity mean I have equilibrium? No, it doesn't. Okay, equilibrium occurs when these stop changing. Thanks, everyone. All right, same reaction, different graph. This graph is about rate versus time. Reaction rate versus time. Now, if we're talking about equilibrium, we do want this to be the same, right? Here's the rate of my forward reaction. Here's the rate of my reverse reaction. If I want to reach equilibrium, I do want my rates to be the same. That is the definition of equilibrium. So I'm looking for that spot where they meet. Okay? So equilibrium is going to get represented one of two ways. Concentration versus time, or reaction rate versus time. Okay? Just make sure you read your y-axis and understand and remember the definition, and you should be golden. What I would do if I were you, because this is on your sheet, right? Although it's kind of like, you know, gray and then a darker gray and then like a darker gray, right? I would maybe circle the y-axis, because that's the difference. That's the thing that you need to look at. That's how you're going to figure out what you got and what you're trying to learn. Okay. Questions there? That's kind of old news. I kind of talked about that already this unit, but figure we bring it back a little bit today. All right, now we got some pictures. Now, this one's kind of annoying. There's, especially, I'm sure on your sheet, it's like extra annoying. How's it look? Oh, it's not too bad. You can almost tell the difference. I said almost. Okay. But pictures involving the correct number of particles can also be used to represent reversible reactions. Consider this. All right, so here is my reaction beforehand. By the way, I'm sorry. Same stuff. Okay, carbon monoxide and water. There's your carbon monoxide. Carbons are the black ones. Oxygen is red. Hydrogen is white. I know on yours it's gray, gray, and gray. But look at my screen and hopefully that helps you. Okay. This is carbon monoxide. This is water. At the very beginning, I have 1, 2, 3, 4, 5, 6, 7 carbon monoxides. 1, 2, 3, 4, 5, 6, 7 waters. Nice. 1-to-1 ratio. Perfect. That's good because the balanced equation has a 1-to-1 ratio. Now, as this reaction starts to happen, okay, this is like time. You see how like I have 4 pictures, right? It's like a time lapse. Here's the beginning, the initial. Nothing but the reactants, carbon monoxide and water. I shift over 1 box. Time has progressed just a little bit. What's going on? Well, now I've produced some product. There's the hydrogen gas, and there's the CO2. Okay, those are the products. So we've started to make product. I've got 2 carbon dioxides, I've got 2 hydrogens created. The good news is everything is 1-to-1 to 1-to-1 in this picture. When you get different ratios, you got to be careful, right, not to miscount. For example, if I had a coefficient of 2 for the carbon dioxide, I would need to make sure that I am counting 2 of those for every 1 of the other. Just cautioning you. Okay? We keep going forward further. Hey, look, we've made more product. I now have 5 of each of my product molecules and just 2 of my reactant molecules left over. And I keep going further, and I still have 5 of my product molecules and 2 of my reactant molecules. Okay, so from time point C to time at D, what has changed between these 2 pictures? Literally nothing. Meaning the molarities have not changed at all, right? So I would say if this picture were trying to, ask us something about equilibrium, I think we can interpret that at point C, equilibrium has been reached. Because anytime after that, D, we have the same molarities or the same concentrations of all the species in our solution. Okay? So same concept, just with pictures. Okay? What's really important here, right, is we're not looking for equal quantities. We're looking for molarities stabilizing or molarities going unchanged, because that represents equal rate. Okay? I've got some notes underneath, right? So A, equal moles of the 2 reactants are mixed together. B, they form some product. After time has passed, equilibrium is reached at point C, and then nothing changes in point D. Okay, so there's a little caption there for you to hopefully figure it out. All right, 7/8's done. It's at 5 minutes. I think that was maybe 7. Okay. Pictures, that's all 7/8 was. Okay, can you count atoms? Can you interpret a picture? Can you interpret a graph showing equilibrium? 7/9. Le Chatelier's principle has this fancy little caret over the A. I don't know what that's called. I'm not sure what it does to the pronunciation either. I don't speak Frenchy. I only know, what do I know? Fromage, isn't that cheese? An important word to know. About all I got. Bonjour. Oui, yep. ¿Qué pasa? ¿Dónde está el queso?
What did you just say?
Where's the cheese?
Only Spanish.
I know cheese in every language, that's all I know.
I don't know cheese.
What's cheese in German?
I don't know. I lie. I don't know.
It's probably this long of a word.
In what?
Everything in German is that long.
Yeah, it's that long.
Because their language rules in German, can't you just literally just keep tying words together?
Really?
Yeah. I took German for 3 years.
Thank you. That's
Oh.
important to know. These are good, valuable life skills that I'll need.
There's a word that's 100 and some letters long.
That's what I mean. There's YouTube videos
And
about
it-
how
it
the German
literally
language
just
works.
means, a
Weird.
whole-
That's
in
when
a
you speak
Harvard,
English.
in a specific Harvard
Yeah.
cross. It's
I think I've seen that one.
Isn't
Yep.
English the hardest language because of all of our little
yeah.
gimmick
Well, and I-
create?
Because the English language is just multiple languages used together.
Yeah, it's a hybrid
We
language.
don't
It's
have
not
any
not
accents
organic.
that we put on letters, but we pronounce them differently as if they do.
And yeah, the English I don't know. I could be wrong, but doesn't the English language have more just flat out words?
Probably.
I think so. I mean,
We
if
talk a
you're
lot.
talking just characters, probably Mandarin beats this out. I think that's.
Okay.
Just because you can't it's just as much symbols and stuff.
I heard that Norwegian is the easiest second language for English speakers to learn. And I'm like, really?
I've never,
I'm not familiar with the Norwegian language. But I'm like,
never.
I feel like those Scandinavian ones got this, I don't know, they're kind of
Yeah.
they're kind of scary. But apparently, if you want to learn a second language, apparently Norwegian is very easy not easy, I should say, but easier than other languages for an English speaker to try to learn.
The more you know.
Like, the more you know.
Where else would you learn this information? Not English.
Yes.
Chem class, maybe.
Le Chatelier's principle. This is from last year. This is the same definition from last year. That's why I have it written down, because I don't want to screw it up. A system at equilibrium, when stressed, will shift to lessen the effect of the stress. Here's what that's trying to say. We have a reversible reaction, and the reversible reaction has reached equilibrium. At that point in time, we're going to mess with it. Okay? Equilibrium has been established, and now we're going to stress it. Okay? How can we stress it? Well, we can change the temp. We can add more stuff or take some stuff away. Right? I can add product, I can add reactant. I can remove product, I can remove reactant. I'm going to mess with it. I'm going to stress it. And the equilibrium, as a result, will shift to reach a new equilibrium. Okay? That's Le Chatelier's principle. You talked about this last year. You did a bunch of worksheets on this last year, I think. So equilibrium has been reached. Now let's stress that system and see what it does. Okay? And by stress, I'm talking about chemical changes, changes in concentration or molarity, temperature changes, pressure changes, okay? Different ways of just messing with the system. So, these tables may or may not look familiar to you. I have this gigantic, weird, crazy reaction. Okay, that's a redox reaction. I like redox, it's good stuff. I kind of miss it. We'll bring it back in unit 9.
Let's go. There's like two sides.
There's like, no, there's one side. There's like
I heard
sarcasm.
yes.
There's sarcasm and then silent, but in the back of their head, like sarcasm.
That's true.
Yeah.
This ain't my first year teaching. Plus, I'm not old enough to be naive enough to know, anyway. Okay, so here's our reaction. It's at equilibrium. We are at equilibrium in the beginning. Okay, this is different than K versus Q, right? K versus Q the last 5 days was, here are some starting conditions. Now it's going to shift, go to equilibrium. In this instance, for Le Chatelier's principle, we're starting at equilibrium, and now we're going to mess with it. Okay, so here is the stress. In this first row, we're going to add extra permanganate, MnO4. What is that going to do to the equilibrium? That's the question. Now, a couple things of note. The same rules still apply that we've had earlier. Aqueous and gaseous things matter. In other words, things that are aqueous in solution or gaseous can be affected by shifts in the equilibrium. Things that are liquid and solid, don't have any of those, cannot. Now let's get a funner color. I'm sorry. I like purple. Purple's a good color. I'm a fan.
My favorite color.
I think it is mine too. I like it.
Yeah, I'm holding it.
Wow.
Wow.
Brutal. Brutal.
Okay, so here's the stress. Now, the way we're going to fill this in is we're going to use arrows, ups and downs and lefts and rights. Okay, so the first thing I'm going to do is I'm going to put in the arrow for whatever my stress is. I'm adding MnO4. Okay, that means the molarity of the MnO4 is going to go up. That's what I am doing. It is going to increase because I am adding more. The next arrow that we're going to put in this table is the shift. If I add more reactant on this side, which way do you think my reaction is going to shift? That way. I've got to rebalance it out, right? We want to reestablish equilibrium. If I add more of the reactants, well, then I'm probably going to shift and make more product. Absolutely. Now, the rest of these are going to get filled in based off of the direction that we're going. Okay? Couple things. Again, water is a liquid, right? What's going to happen to the molarity of water if it's a pure liquid? Do you know? It doesn't change. We're going to write NC, meaning no change. It doesn't matter, okay? The molarity of pure substances, pure liquids and pure solids, are unchangeable. So regardless of whether we are shifting right or left, the molarity of water, because it's a liquid in this instance, will not change. So we can preemptively just write that in. Okay, I'm shifting to the right. What's going to happen to the molarity of this reactant if I'm moving from reactants to products? It's going to go down. We're going to use it up, right? What's going to happen to the molarity of the other reactant right here as I shift left to right? This product, energy, K value. What's the K value? It's the equilibrium constant. Products over reactants. Now, this is going to sound weird. Okay? This is going to sound weird. The value of the equilibrium constant is constant.
Wow.
Unless you mess with the 10. Okay? That may ring a bell.
Oh.
If you change temperature, your reaction is occurring under different conditions and the equilibrium constant will be different. But if you're just adding or taking away substances, it has no effect on the constant K. In other words, we're adding something, temperature's the same, the value of K will not increase or decrease. That sounds weird, because if you look at it, right, what are we doing? This reactant's going up, those reactants are going down, so we have like two things fighting each other. The products are all going to go up. But again, the ratio of these shifts are equivalent, meaning that even though this has gone up, those have gone down, these have gone up, in the end, the ratio, or the fancy ratio of products over reactants, is an unchanged constant value. Okay. So is the shift going to be very large when we say it's shifting? Usually it's really, really tiny. Okay? It's just a tiny shift to reestablish equilibrium. But we're not looking at numbers. This is all just conceptual, right? This is all just, in theory, which way is it going to go? Not doing any math. Let's do another one together, and then I'll give you a shot at the rest of these here. Removing carbon dioxide. The very first arrow I want to put in is the arrow of my stress. What am I doing? I am removing something. Okay, that means I am forcing that to go down. That's what I have messed with. That is the stress. As a result of that stress, which way does my reaction want to shift to reestablish equilibrium? I got to replace what I just took away, right? I took some stuff away. I have removed some product, and as a result, the equilibrium is going to shift to replace what I just took. That's the opposite of the first one, right? The first one was I added extra stuff. I added reactant, and as a result, I needed to make more product to balance it out. This one is I am removing product, so I need to shift towards it to replace what I just took. No. Depends on what you add or remove. For example, if I add water, right? Actually, that's not a good example because water is liquid. If I add manganese, that's a good example. If I add this stuff, right? I have added product, so which way do I need to shift? To the left.
It's just like it's kind of like an hourglass, like it just like wants to be even.
Yes. Yeah, here it's a
Or
seesaw.
not an hourglass, it's a seesaw.
Yeah. Or if you're from Boston, a tita tata.
That's one.
Thanks. Sounded sincere. Okay. Yes, it's a seesaw, right? We need an imbalance. So if I have added something on one side, I want to shift and make more on the other side. If I've removed something on one side, I got to replace what I just removed to get it back into balance. Yes. Okay. So I removed the CO2. That's a product. Product side went down. Let me make some more. We shift to the right. And then as a result of this shift, we can fill in all of the other boxes. Any other reactant, I'm shifting from left to right. I must be using this up to make more product. I'm using this reactant up to make more product. I'm using this reactant up to make more product. And then I'm making more product, so my energy increases. And what happens to the K value?
No change.
Did I mess with temp?
No.
Nope, so no change. Try the next, well, what happens when you add water? Nothing happens. Why? It's a liquid.
Why did the energy go up for the last one?
The energy term's right here. Meaning, like,
Oh,
it's a product, basically.
yeah.
You can treat it just like any product or reactant and it shows up. Okay, try the next two. Maybe that's a little better. Ooh, actually, this one's more fun.
Yeah, there's no.
There isn't any NaOH.
Which
Oh.
side do you add it?
Yeah.
It'll be a reactant.
Yes.
We have a side reaction going on. Who said that?
That's what you're saying.
Yeah, who did?
Huh?
Yeah, she said, yeah, I guess.
Yes, yes.
Yeah.
you told me that. I was like,
And I accept that, I've always accepted that. Again, ask any parent or adult about chemistry and their first reaction is usually something like, oh.
Anytime I've ever asked my parents for anything about school, like I stopped asking in elementary. Because they were used to stuff. But every time they were just, oh yeah, I did my time, I hate that.
Did my time.
It's like basic, like fourth grade math, was it, yeah, just isolate the variable thing, very simple, but this is annoying, there's 30 problems of it, my mom and dad, it was literally just do this. I don't know how they did. Like, any of the old math, huh? All they talk about is the old math, I don't know what that is, it's like they're talking.
Well, yeah, I mean, math,
The old map.
I think math used to be just like, you know, don't you get it? And it was either a yes or a no, like literally, it was either like, does that make sense? Like,
Now it's so.
now it's all like convoluted and like they try to like use systems and, I don't know, the problem was I got that, right? Like when I was a kid, it's like, oh yeah, that makes sense, like, easy. But now they're trying to like make sure there's more kids understanding math.
That makes sense, I guess.
But then they, yeah, then they teach everyone the same systems and
And
it's
then they
really.
add them up all separate, I was like,
Did you have to learn about frictions though? Did
Is that?
you have to learn about frictions?
Yeah, I did geometry. Yeah.
I don't even know what that is.
Add manganese. Is manganese one of my columns? No, so normally what I've said, right, is put the stress arrow in first. We don't have a choice. It's not there.
well, it's like, it's in the products.
Yeah, it's here, right? It's here, but it's not in my data table. So, yes, Sam?
Technically, you have products that would make product the reactant product.
I understand what you're saying,
But it's like.
So why would you say that?
because then that's confusing. I will say that this side is the reactant side and this side is the product side, even if, yes, we are shifting from right to left. Because I don't want to switch the definition of what I'm calling each side.
Changing chemistry.
Well, no, that would be confusing. I don't need any help confusing you guys, I'm pretty good at it. Manganese, that's a product, right? So I am adding product, which way do I need to shift? Left. I need to balance that out. I need to make more reactant to balance out the product that I've added. As a result then, this reactant will go up, this reactant will go up, this reactant will go up, this product will go down, the energy will go down because it's on the product side, and what happens to K? Nothing. We didn't change to 10. Add sodium hydroxide. Did anyone figure this one out yet? Acid-base reaction. What's that stuff?
Oh. Sneak.
Who did that?
That's an acid, right? So if I add sodium hydroxide, what's it going to do? It's going to react with the hydrogen ions on the left. And as a result, it's going to remove those or neutralize those, right? So the molarity of the hydrogen ions is going to go down. So it didn't say that, right? It's not directly giving you the stress this time. But in theory, if you kind of, think a little bit and contemplate what that would do, well, this is a base. We have acid. Those are going to react. And this base will neutralize that acid. Therefore, this molarity is going to go down. And as a result, we would shift towards it to replace what we just neutralized. Yeah, dear.
Okay, so with the acid basis thing, it's not like a product or reactants, it's just wherever the acid base is.
Correct. Yeah.
So
So,
like if the hydrogen was on the product side,
Yep.
it would.
yep, you got it. Yep. So we're going left, meaning the other reactants are going to increase. My product is going to decrease. My energy will decrease because it's also a product. And did I change the temp? Nope. Okay. Increased temperature. Ooh, now we change the temp. How exciting. If I crank up the temp, how can I account for that in my equation? Correct. Now, what's weird is energy comes in many forms, right? This is where no one has asked the question yet, but let me talk for just a second, right? Do you see how I'm saying energy is going up and energy is going down over here? Yeah. Energy can change without a change in temperature. Okay? Energy can change without a change in temperature. But when we change the temperature purposefully, that's also related to energy as well. See what I'm saying? So don't let these little changes in energy screw you up. It's kind of the weird thing because we're using energy in both contexts within the same table. An energy change where temperature is increasing or decreasing, and energy changes where temperature is not increasing or decreasing. Maybe I've made it worse. I don't know. But we increase temp, meaning we have increased the energy in our system. And therefore, we are going to have to shift which direction? To the left. As a result, the reactants are increasing, the other product is decreasing, and K does change. Ooh. What is K again? Equilibrium constant, products over reactants, right? What are we making more of?
Reactions.
We're making more of the denominator, the reactants. So what's going to happen to the value of K? It's going to get smaller. Okay? Now, be very, very careful. This is where kids like to go on autopilot. If you increase temp or if you decrease temp, that does not tell you how K is going to change. If this were endothermic, right, where the energy is on the left-hand side or the reactant side, an increase in temp would increase K. Okay? So you cannot assume that a change in temperature affects K the same way every time. You can increase the temperature of one reaction and K gets bigger. You can increase the temperature of a different reaction and K will get smaller. It's not about whether the temp goes up or down to determine how K changes. It's everything about which way are you going. If you are shifting to the reactant side, K is getting smaller. If you are shifting to the product side, K is getting bigger. Because it's a ratio, right? Products over reactants. Am I making more products or am I making more reactants? Making more reactants. Okay, K must have gone down. Make sense? Cool. Pressure. What's pressure, Nesmith?
Oh, yeah.
Gases, right? How many things are gas in this reaction? Just the product. I have 10 moles of gas on the product side. I have 0 moles of gas on the reactant side. If I'm increasing the pressure, I'm kind of squeezing my, like you can think of it like a sealed chamber, right? Yes, Jigger?
It says decrease pressure.
Oh, I'm sorry, thank you.
Just wanted to stop.
No, you're good, thank you. If we decrease the pressure, let's do the opposite, okay? We're giving more volume. It's better to think in terms of volume when it comes to pressure in these instances, because it's just, the visual makes more sense in your head, right? Here's the deal. A decrease in pressure means I'm providing extra space. If I'm providing extra space for the gases, I'm going to make more of them. The opposite is probably more intuitive. Let me give you the opposite scenario, right? Let's say it were an increase in pressure. If I increase pressure, I'm smushing it, right? I'm making it smaller. I'm shrinking the volume. And there's less space for the gas. So what would happen? We would want to shift to make less gas. On the opposite, if I decrease pressure, I am increasing the volume, and therefore there's extra space, more space, so we're going to produce more gas. See what I'm saying? Okay, so we are shifting towards the gas. 10 moles on the right, 0 moles on the left. We will shift to make more gas if we decrease pressure. As a result, the reactants will all decrease, the products will increase, and K will go unchanged. You did some of this last year, right? Cool. 2 years ago, thanks, Dylan. Here's some more. I'm gonna chill for a second. Go for it. See what you can do. feel free to check with your neighbor.
I don't know if that's.
Yeah, if you are. Did everyone get their name on here? Oh, yeah, I suppose that makes sense. Hey, Aiden, how much of the board can you see? All right. Are you okay sitting there?
Yeah.
Okay. You pay less for those seats at Miller Park. Yeah, so it's all one. So, how many? And this is increasing pressure. It's all about, again, like, it's all about that stress, right? So if I'm decreasing volume, I'm squeezing down on those gases. So if the need there, it would shift to less gas. Sorry, that's probably like a giant wall of impossible to decipher. Please ask questions. Would you like me to? Here. Where is it? Would you like me to go row by row? Does that hurt your eyes less? Okay. First one, oxygen goes up, we shift to the right. That's the first number I put in. That's the second arrow I put in. All the other ones change based off of that. Questions there? Removing NH3. Questions there? Yes, Ben?
I have a question about the first one.
Yeah.
So for the energy, the idea is you extract the energy, so put the temperature.
Sure. Yeah, sure.
Is that it or what?
No, again, this is hypothetical, right? This is very hypothetical. Here's the problem. If we were doing this for real, if I had this actual reaction actually at equilibrium, and I actually added anything or removed anything, that energy change will change the temperature. So the truth of it is the temp's going to change. But on paper pencil,
If you could keep temperature the same,
yes,
then
correct. Correct. So on a paper pencil version of this, we're assuming that life is really nice and neat and we don't have all these other variables going on. In a lab, yeah, if we were actually running this and monitoring it and messing with it, any energy increase or decrease would change the temp. So we
yeah, in a container of really conductive, a lot of thermal conductivity, then it would be closer to these results, because it would get, you would extract the energy.
sure. It's all hypothetical. I mean, again, this is the paper pencil version of the concept, not the actual lab execution of the concept. Adding water, questions there? I think the adding and the removing of stuff, that's the easy ones, right? I really think. The temp or the pressure ones you might have to think about a little bit, but I think if, hey, I added some of this, I took some of that away, that's generally pretty friendly. Okay, the temp decrease, again, my energy term is on the product side this time, so a decrease in temperature would take energy away. As a result, I would shift to replace what I've removed. The reactants go down, the products go up, and the K value changes. Now, K is going to go up. Why is K going to go up? Because of that, the shift, right? It has nothing to do with whether temp has gone up or down. Nothing at all. It has everything to do with, am I making more products or am I making more reactants? If I'm making more products, my ratio of products over reactants gets bigger. If I'm making more reactants, the ratio of my products over reactants gets smaller. So it's everything to do with the shift, nothing to do with increase or decrease of temp. Pressure is all about gas. In this one, I have 9 moles of gas on the reactant side. I have 10 moles of gas on the product side. So I am increasing pressure, which basically means I'm decreasing volume, right? I'm like squeezing this reaction chamber down. And as a result of that less volume, less space, this is going to want to shift to relieve that stress, right? It's going to want to shift towards less gas to counteract that increase in pressure. So we shift left. Everything changes according to that shift. Anything at all? Rings a bell, I hope, right? It's not too bad. Again, the where you can screw it up is not putting the arrows in the correct order. What I mean by that is your stress should always be the first arrow you put. Your shift should always be the second arrow you put. And then everything else changes off of that. Okay? Always put your stress arrow in the first spot. Always put your shift as second, and then deal with the rest of it later. Is that it on this slide? Sweet. Okay, this is review. Top part is anyway. Okay, go ahead, set up the equilibrium constant expression. K equals some stuff over other stuff. Oops. Right, nothing special there, we've done that a bunch of times. The one thing you want to be cautious of is using the appropriate value of K. This is Kp, these are all gases. So we'll totally use the partial pressure of these things. And when we write out partial pressures, we're not using brackets. Brackets imply molarity. These are not molarities, these are partial pressures. So capital P, subscript, whatever it is, raised to the power of its coefficient. Okay. At equilibrium, the partial pressures of each gas is listed below. Determine the value. Okay, let's load the stuff in. Go ahead if you have not done so already. What do you forget? Value of K. Assuming somebody's on. Okay. Pretty sure that's right. My brain's telling me it is. We'll get a double check though. Yeah? You're good. Okay. That's old news, right? We've done that a whole bunch too. Hopefully that's still nice and easy for you. How many total moles of gas are in the 10-liter flask at equilibrium if the reaction is at room temperature, or sorry, at a temperature of 25 degrees Celsius? How's that one going for you? What are we trying to solve? Trying to solve for moles. What do we know? Volume, temperature.
Pressure.
We can solve for pressure. Because if I add up all of the partial pressures, I get the total pressure, right? So I know pressure, volume, temperature. And I want to solve for moles. What equation do I need? I need the ideal gas law equation, PV equals nRT. I know 3 of those things. I want to solve for the 4th. Excellent. We can totally do that. I'm kind of out of time. We'll pick this up tomorrow. Tomorrow we'll finish this thing off with E. And then, yeah, then we'll get real spicy. Did you do the last one?
I couldn't get it.
Okay.
Mhm.
Well, I'm glad I sunk you a little bit there.
It was like, I thought,
Yeah.
is that the right setup?
Yeah, Jimmy, good.
I'm gonna do it now.
Well, that's good.
I have nothing to do.
No.
Mr. Elliott completed his test really fast.
Yeah, I sound like a floor.